There are two kind of aspects to this lesson in terms of what's important to a student. One is there's a whole bunch of information about this thing called the unit circle that you need to know for exams. Okay, it's non-negotiable. The other is there's a side to this lesson that deals with the unit circle, which if you have a really, really deep and good understanding of, makes your life so much simpler from here moving forward. Okay? It's not critical. Some of you may find ways to, when I'm talking about that side of the lesson, you may find ways to work around having that knowledge. But if you have that knowledge at your fingertips, life becomes much better. Much, much better. We've got enough to worry about in trigonometry in 30-1 without saying, oh, well, I'll just rely on some other things that I hope to figure out. What you want is a really solid understanding of the unit circle. So we're going to be looking at the equation of what's called the unit circle once we define it. We'll also briefly talk about equations of other circles. When I'm talking about an equation of a circle, I mean an equation connecting x and y so that if you could graph it, you'd see a circle. Now you can't graph a circle on your calculator because a circle is not a function. It would fail the vertical line test. And the only things you can graph on your calculator are functions because they're y equals. Then this is what we're going to spend the bulk of our time on, finding the coordinates of points on the unit circle for angles that are multiples of all of these common angles. In other words, if I were to sketch the unit circle, it's a circle centered at the origin. We'll get to the details of it. And I draw a rotation angle of 315 degrees. That terminal arm, which has an arrow on the end of it, extends forever. It'd be in quadrant 4. And it's going to intersect that unit circle. It's going to intersect this circle. At the end of this lesson, you should be able to tell me that the exact values of the coordinate pair of that point of intersection at 315 degrees is the square root of 2 over 2 for x and the negative of the square root of 2 over 2 for y. You should be able to tell me that when you go to 7 pi over 6, which would be in quadrant 3, that the coordinates of the point of intersection of that terminal arm and the unit circle will be negative root 3 over 2, comma, negative 1/2. And you might notice when I said that, I closed my eyes and my eyeballs rolled up. That's not because I'm searching my memory for what they are. I'm figuring out what they are. Okay? And then once we're done that, the question that students have is, who cares? What's the big deal about these coordinates? Well, it turns out that they are significant in terms of trigonometric ratios. So to begin with, the unit circle is a circle of radius 1 unit. This is why it's called the unit circle. The radius of this circle is 1, and it's centered at the origin. So if you take a look at this diagram, there's a nice picture of the unit circle. I'll get to the rotation angle that's shown in a second. But I do want you to note, and this will be important for later, that you already know the point of intersection of the terminal arm and the unit circle when theta is 0 degrees, when theta is 90 degrees, when theta is 180 degrees, and when theta is 270. The point of intersection at 180 degrees is negative 1, comma 0, because you know the radius is 1, and at 180 it's a negative value for x. And at 180 that point lies on the x-axis, which means the y-coordinate is 0. So what I'm telling you is that thing that I described, namely the points of intersection of terminal arms in the unit circle for special angles, you already have that knowledge for some of these angles. All you have to do is know that the unit circle has a radius of 1. The first question says, if we take a rotation angle, theta, and we look at the point of intersection of the terminal arm and the unit circle, there's a point there. The coordinates are x, comma, y. When we draw this, what we very often don't show is that that terminal arm goes on forever. But it does go on forever. But I just want us to focus on that point. And the first question says, how are x and y related to each other? There is an equation that connects x and y. If you knew x, you could calculate y, and if you knew y, you could calculate x. Does anybody know what the connection is? Well, I'll give you a hint. There's a right triangle right there. And the base of that triangle is the x-coordinate and the height is the y-coordinate. This is actually math 20-1, kind of, with a twist. What's the connection between the two short sides of a triangle that's a right triangle? X squared plus y squared equals the hypotenuse squared, but it's a unit circle. The hypotenuse is 1. Do you remember last year doing this? Maybe a vague recollection of doing this last year where we had x and y, but that length was called r. And we defined sine, cosine, and tangent in terms of x, y, and r. Well, that's kind of where we're going, but r here is 1. So what is the relationship? It's the Pythagorean theorem. It's x squared plus y squared equals 1 squared, which simplifies to x squared plus y squared equals 1. And I want to make a point to you. This is the equation of the unit circle. So if you had the ability to enter x squared plus y squared equals 1 in your calculator and say graph it, it would graph a circle. But the thing I want to point out to you is, and you have to listen to the words carefully here, otherwise you'll miss my meaning. The equation of the unit circle is not x squared plus y squared equals 1 because the radius is 1. It's x squared plus y squared equals 1 because the radius squared is 1. Right? I don't want you to get a misconception here that if the radius were 5, it would be x squared plus y squared equals 5. And that'll be shown in the next little bit of business that we talk about. How would the equation in A above be different for a non-unit circle centered at the origin if the radius was 3? Well, you know, and this is kind of why I drew this arrow here, is this extends out forever. So if we just blew that circle up and talked about a new point with coordinates x comma y, that point would be 3 away from the origin. So you'd be dealing with a triangle which would be 3 times greater. Of course, that's still x and that's still y. So the equation would be this, x squared plus y squared equals 3 squared. Which means x squared plus y squared is equal to 9. What if the radius was r units? So let's just go, we went from very specific with the unit circle to a specific case that's not the unit circle. Well, what about the most general case? As long as it's centered at the origin, the equation of the circle will be x squared plus y squared equals r squared. So if the radius is 1, the relationship between x and y is x squared plus y squared equals 1. Very simple relationship to work with. But that means it's the unit circle. If it's a non-unit circle and it's centered at the origin, then x squared plus y squared will equal r squared. Does that make sense? Both of these things, the x squared plus y squared equals r squared and the x squared plus y squared equals 1, form the foundation for a lot of what we do in this unit. So example 1, the x-coordinate of a point on the unit circle is 3/4. What's the y-coordinate, and sketch the rotation angle? And I've given you, 2 diagrams here because there are going to be 2 rotation angles that have an x-coordinate of 3/4. Just look up here. You don't need to mess your diagram up or anything, but where is x equals 3/4? Well, x equals 1/2 is probably, I would say x equals 1/2. I could get out a ruler, but I'm not going to waste my time with that. Is probably there. Would you agree? Which would mean x equals 3/4. I can get this thing to go. Well, I'll just move it. Is probably about there. Would you agree? I mean, I'll put a ruler down here just so we can see. So that's 1. I was a little bit off. Maybe a little bit further to the right. But that's not the point. The point is not that we need to have things perfectly aligned here. The point is that there will be a point on the unit circle here and another point on the unit circle here that each have an x-coordinate of 3/4. There's 2 points. And this is going to lead eventually to the fact that when we solve an equation, there's going to be 2 solutions very often. Because don't forget, these points are points of intersection of a terminal arm of a rotation angle. There's angles associated with these points. The angle associated with this point it doesn't matter. Try something new for a change. The angle associated with that point will be this, and the angle associated with this point will be that. We're not trying to find the angle. Okay, that's not the point. So what are the y coordinates? Well, x squared plus y squared equals r squared. But it's the unit circle, so r is 1 and r squared is 1. We can put the 3/4 in for x. So y squared will equal 1 minus 9/16. Just take a minute and percolate on that and how I got 9/16. 3/4 squared. You square the 3, you get 9. You square the 4 to get 16. Well, 1 is 16/16. 16/16 minus 9/16 is, last I checked, I believe 7/16, correct? If you need to do that on your calculator, that's fine, but I end up with y squared equals 7/16, which is a little bit less than a half. That means, finally, y is equal to plus or minus the square root of 7/16, which is plus or minus root 7/4. You know, I just want to back up here. Up here I said, well, which is a little bit less than a half. That's of no consequence. That doesn't mean anything. What we're interested in is the y coordinate, not y squared. So root 7/4, if we were to label this point now, this point would be 3/4, comma, root 7/4. This point would be 3/4, comma, negative root 7/4. Are you with me on what we did with that? Okay, any questions with that example? Y coordinate of a point is that, -1/√2, and the terminal arm lies in quadrant 3. I know it says the point is in quadrant 3, but that's the same as saying the terminal arm is in quadrant 3. What that does is removes all ambiguity about the y coordinate. The y coordinate will be negative. You're told it's in quadrant 3. In quadrant 3, x and y are both negative. It removes all ambiguity about the x coordinate. We're given the y coordinate, aren't we? Okay. So I want you to do something for me just now before we get going with this example. Take your calculator and take 1 divided by the square root of 2. And I realize that the number you're looking at will not be an exact value. It's a decimal approximation of an irrational number. But would you agree it's approximately 0.707? Okay. What I would like you to do now is take the square root of 2 divided by 2. And when I say that, I mean the square root of 2 end brackets divided by 2. Do you agree it's the same number? So this is kind of like we and yes. If you're bilingual, you understand that those two things have the same meaning. From now on, you really need to understand that something like this may appear as this. They're the same thing. Just so you know. So let's find the x coordinate. It is x squared plus y squared, which is -1/√2. This needs to go in its own set of brackets. Squared equals 1. Which gives me x squared equals, well, I'll do this in steps, plus 1/2 equals 1. Because when I square the -1, I get +1, and when I square root 2, I get 2. If I subtract 1/2 from both sides, I get x squared equals, well, 1 minus 1/2. So x squared is equal to 1/2. 1 minus 1/2 is 1/2, which means that x is equal to plus or minus the square root of 1/2 which, if we break up into the two answers or solutions to that equation, one is positive, one is negative, and it's 1 over root 2. So first of all, since you were told it's in quadrant 3, we can kick this one over the boards, because in quadrant 3 x is negative. And secondly, I want you to know, or notice, this is the same as the y coordinate, isn't it? And this will be useful for later. The only way the x and y coordinates can be equal, I mean, I'm just going to put a point here. Would you agree that the x and y coordinates are different there? The x coordinate is quite a big negative number, and the y coordinate is a smaller negative number, looking at the size of the number, not the direction. And I hope you would agree that over here, it's out of balance as well. That tells you that whenever you see either an x or a y coordinate that's 1 over root 2, or negative 1 over root 2, or root 2 over 2, or negative 2 over root 2, you're going to be talking about a 45-degree reference angle. This point will be exactly the same distance, angularly speaking, or along the arc. It doesn't matter how I describe it. Exactly the same distance from the x and y axis. So we can label the points here. The points are negative 1 over root 2, comma, negative 1 over root 2. Do you remember that I said a big objective here today is for you to be able to know the coordinates of all of the points of intersection of common angles? Have we answered this question? We haven't sketched the rotation angle yet. The rotation angle is this. And although you were not asked for the rotation angle, you should be able to determine that it's 5 pi over 4. 1, 2, 3, 4, 5 pi over 4. Right. So now we're going to build the unit circle, step by step. When we talk about a specific point on the unit circle, we use certain notation. We use p of theta. So, for example, if I talk about this point that corresponds to the point of intersection of a terminal arm and the unit circle when the rotation angle is 30 degrees, that point is called p of 30. Okay? All right. Let's figure out what p of 0, p of pi over 2, p of pi, p of 3 pi over 2, and p of 2 pi are. All I'm asking you is what are the coordinates on the unit circle where the terminal arm intersects at 0 degrees or 0 radians? Well, I've got this here. We can look at this, but this should be in your head. You should be able to say, well, at 0, the x coordinate is 1 and the y coordinate is 0. If I were to go to 90 degrees, which is pi over 2, the coordinate numbers switch. The y coordinate is 1. When you look at p of pi, the x coordinate is negative 1 and the y coordinate is 0. At 3 pi over 2, the y coordinate is negative 1 and the x coordinate is 0. And then this, of course, we're back to 1 comma 0. And I think that's pretty obvious. I'm not even looking at the unit circle, so I better double check. X is 1, x is negative 1, y is 1, y is negative 1. We're okay. Does that make sense? Okay. So what does it says? Record the coordinates on the sheet titled Building the Unit Circle. So on this sheet, you can put here that that's 1 comma 0. That's 0 comma 1 at the top. Negative 1 comma 0 there. And then, of course, at the bottom, at 3 pi over 2, 0, comma, negative 1. Don't get me wrong. The point is not that at the end of this you're going to have this masterpiece that you will memorize. We're doing this so that when you need to determine coordinates, you know what to do. We don't get this for a unit exam. Okay. All right. Number 2. This is a bit of something that you maybe have blocked out of your memory, but in Math 20-1, you learn about these special triangles. Okay, remember this vaguely? Not what the numbers are, but we're going to use different numbers this time. Okay, so on the back of the sheet titled "Building the Unit Circle," the special triangles, this 30, 60, 90 degree triangle and the 45, 45, 90 degree triangle, are given when the hypotenuse has a value of 1. Now, probably, so I'm going to start with this one. Probably your Math 20 teacher said, let's call this 2. And there's no need to write this. I'm just trying to reinvigorate these memories of doing this. Well, let's call the hypotenuse 2. And you might have said, well, why? And they would have said, never mind why, just do it. Because they know why and you don't yet. And then they said, here is why. Because if we flip this over on itself, what you get is the side of this big triangle of 2. Do you remember seeing this? Okay. Since this is a 60-degree angle, this is Math 20, and this is a 60-degree angle, and this is 30, and this is 30, then this whole thing is equilateral. It's a 60, 60, 60-degree triangle, which means that this vertical side on the right is too tall, which means that this is 1. And then what you would have done is in this triangle, you would have said hypotenuse squared equals 1 squared plus, I'm going to call this x squared, and you would get x squared equals 3. And you take the square root, and you go, oh, this is root 3. So how many of you remember doing this and getting these numbers and doing some limited amount of work with this triangle? It's only to warm you up for this. Okay? The only issue is the hypotenuse matches the length of the terminal arm to the unit circle, and it should be 1. So if you divide all of these highlighted numbers by 2, you get this triangle. Okay, so you should know how to get this triangle if you need to. Don't guarantee anything. I believe by the end of this lesson you will not need to build these triangles. You will know the numbers. Okay? And we also have this triangle. And what you probably were told last year is let's call this 1 and let's call this x. And just for kicks, let's call that x because we know they're equal. And if you use the Pythagorean theorem, you get 1 over root 2 or root 2 over 2. Okay? All right. Use the values of the sides of these special triangles to determine the coordinates of these 3 points. So, what are the coordinates of the point of intersection of the terminal arm and the unit circle when theta is pi over 6? In other words, what's p of pi over 6? Well, if you imagine building that triangle and laying it over top of here, the height of that is 1/2, and the base is root 3 over 2, which tells you the y coordinate is 1/2, and the x coordinate is root 3 over 2. Capiche? Sensing some hesitation here with you this morning. Are you on the same page as me? This is making sense? Okay. It's just me. I want you to make a mental note that whenever on the unit circle an x coordinate or a y coordinate is 1/2 or root 3 over 2, the other coordinate is the other number. These two go together like peanut butter and jelly. If you have one, you have the other. We'll label it on the unit circle in a second. What about this one? Well, if I take that reference triangle that we know about, and I lay it down here, you see that the x-coordinate is root 2 over 2 and the y-coordinate is root 2 over 2, which I think you already knew based on a previous example. So this is 1 over root 2, comma, 1 over root 2. And I'm purposefully just changing lanes back and forth here to get you used to the fact that root 2 over 2 and 1 over root 2 are the same. Okay? Well, here what you would do, well, what I would do is recognize, everybody, that it's not the root 2 over 2, root 2 over 2 situation, right? It's the 1/2 and root 3 over 2 situation. So look at it this way. This is 1. Does that look like a half? No. This is 1. Does this look like a half? Yes. The x-coordinate is a half, which means the y-coordinate is root 3 over 2. We could, if you like, put this on here to demonstrate that. But I think, as I said, you're going to move away from looking at those triangles. So this would be 1/2, comma, root 3 over 2. Just for kicks, what is the decimal approximation of root 3 over 2? It's almost 0.9, I think, 0.866. Well, that certainly makes sense because if you look at the y-coordinate of this point, it's very close to being at the top where it maxes out at 1. If you go back, look at the decimal approximation of this number, and some of you might remember it because we already did this. It's 0.707. Well, that kind of makes sense. That looks like about 0.7. That looks like, when we get up here, about 0.9. When we get down here at 30 degrees, that looks like a half. So you can kind of sort out what these are without using the triangles. Now let's add them to our unit circle. So what do we know now? Well, I'm going to just go away from what we just did and just let's do the whole thing. What do we know about this point, this point, this point, and this point? We know the x and y coordinates have the same amount, except that some are positive and some are negative, depending on where we are. And you should know, and I've already got it up here for you, that it's root 2 over 2, root 2 over 2. So we can put in the coordinates here. We can put in the coordinates down here as well in quadrant 3 at that relative position. We can put in the coordinates over here at that relative position. The only thing that's changing is we have to be aware of when x is negative and positive, and when y is negative and when it's positive. You know, if I had to redesign this lesson, I probably would dispense with the triangles. Well, maybe not totally, but I don't think we need the triangles. Do you agree that p of pi over 6 will be that half and root 3 over 2 pair of numbers? So which is a half? Does this look like an x-coordinate of a half? No, that must be root 3 over 2. Does this look like an y-coordinate of a half? Yeah, definitely. Even if you just sketch a rough circle, unless your circle is like really Picasso-ish, you'll be able to see definitely where x or y are a half. And by the way, you are not allowed to bring a compass into exams to draw circles, but you were allowed to have a coffee cup. Draw a nice circle so you can be sure, right? Anyway, that means the x-coordinate is the bigger of the two numbers, root 3 over 2. I'm going to jump off to the other side here, 5 pi over 6. Well, I know that basically, everybody, all of these positions I'm going to highlight in green are all ones that involve 1/2 and root 3 over 2, right? So if I go over here into this position at 5 pi over 6, and I just look at this, I'm just drawing this so you can see what I'm thinking of. Does that look like an x-coordinate that's negative a half? No way. Does it look like a y-coordinate is positive a half? Yes. So the y-coordinate is 1/2. The x-coordinate is negative root 3 over 2. Are you guys picking this up? 'Cause this is what I mean when I said, what are the coordinates of 315 degrees at the beginning of the lesson? And I said, oh, well, I know it's root 2 over 2 comma negative root 2 over 2 because I know I'm looking in quadrant 4 at this yellow point. These ones up top, they're just the opposite numbers here, right? Except that, x is still negative and y is still positive. Over here, instead of being root 3 over 2 comma a half, it's backwards. So take a minute and sort that out in your head and get them all recorded. Quite frankly, like I said, I don't care if you record them. This is a learning activity. This is something that from here on in, I say, what are the coordinates at 11 pi over 6? You do this. Don't look there. 11 pi over 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, that's negative a half for y and root 3 over 2 for x. And I'm glad to see that most of you, as you're completing this diagram, are completing it on your own. You're not looking up here and copying the numbers down. If you are, that's fine, but you have to be able to do it on your own. And I think copying them down or just double checking to make sure that your thinking is right is a good idea. Are we okay with that? Okay. All right, so we've built the unit circle. So far, so what? Well, here's where it ties into trigonometry. In Math 20-1, you learned these two new definitions of sine and cosine. I hope that's memorable. When we talked about coordinate trigonometry, we said let's forget about opposite and adjacent and hypotenuse. For opposite, we're going to use a y-coordinate of a rotation angle's terminal point. And for adjacent, we're going to use the x-coordinate, and then the hypotenuse, of course, is equal to r. This was actually given to you on a formula sheet last year, along with tangent of theta is y over x, which we don't give you any of that this year. On the unit circle, r is 1. That means that the cosine, if we make r equal to 1 here, sine of theta is y and cos of theta is x. These numbers that we're finding are not just the x and y coordinates, they're the trigonometric ratios. Cosine of theta gives you the x coordinate, sine of theta gives you the y coordinate. Take, for example, on your calculator, we'll go in degree mode. (135 degrees is that. Take the cosine of 135 degrees. You get negative 0.707, which is negative root 2 over 2, which is the x-coordinate at that point. Take the sine of 135 degrees. You get positive 0.707, which is root 2 over 2. Well, it's the decimal approximation. Okay, let's take a look at some further examples now using this. What I'm telling you is that the point of intersection of any terminal arm and the unit circle will always have coordinates of cos theta, sine theta. This is one of those non-negotiable things. You need to know this. So, the terminal arm of a rotation angle intersects the unit circle at some point. The rotation angle is negative 75 degrees. What's the value of cos of theta? Okay. We're just going in degree mode. We're taking the cos of negative 75. It's this number. To the nearest hundredth, 0.26. What is the value of sine of theta? Negative 0.97. What are the coordinates of point P? These numbers that we get are the coordinates of point P. So if you wanted to write to the nearest hundredth, it would be 0.26 comma negative 0.97. The point is given negative 0.8 comma m as a point of intersection on the terminal arm of a rotation angle. What is the exact value of m and what is the exact value of sine of theta? Well, m is a y coordinate, so we can write x squared plus m squared equals 1. We want this as an exact value, so can you confirm that when you square negative 0.8, you get 16 over 25? Okay. So that means that m squared equals 1 minus 16 over 25. One is 25 25ths, so if we subtract, we get 9 25ths. Correct me if I'm wrong there. You maybe want to run it through your calculator. 1 minus 16 25ths is 9 25ths. That means that m is equal to plus or minus the square root of 9 25ths. So m is equal to 3/5 or negative 3/5. What is the value of sine of theta? These numbers, because y is the sine of the rotation angle. You don't have to do anything else. So sine of theta is 3/5 or negative 3/5. Can somebody just check? I didn't say anywhere in this question which quadrant it was in, did I? No? Okay, good. That's it. Well, the same kind of thing here. It's changing it a little bit. This is the y coordinate, and you're asked for the x coordinate. That's it. The interpretation here is that since you're told sine of theta is 3/5, and it's on the unit circle, that means that the y coordinate is 3/5, or 3/8 rather. So we can write x squared plus 3/8 squared equals 1. I'm just going to pick up the pace here. Do me a favor, take your calculator, go 1 minus, in brackets, 3/8 squared, and convert it to a fraction. I believe you're going to get 53/64. No? No? 55/64. Thank you. That means that x is equal to plus or minus root 55 over 8 because root 64 is 8. It's in quadrant 2 though. This is why I asked in the previous question, does it actually say which quadrant it's in? Because if it's in quadrant 2, x is negative in quadrant 2, which means that the answer to the question is x is negative root 55 over 8. But that's cos theta, right? I'm not going to write it again and say cos theta equals that number, but x and cos theta are the same thing on the unit circle. And finally, determine the exact value of the coordinates of the point of intersection here. So if you were on your game, and I don't want you to look at your unit circle, what I want you to do is figure out where 10 pi over 3 is. One pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3, 8 pi over 3, 9 pi over 3. 10 pi over 3 is this angle down here. Not the 45-degree one in quadrant 3, but the one that's 60 degrees away from the x-axis. So what are the coordinates? Negative 1/2, comma, negative root 3 over 2. So what I am doing, everybody, is I'm locating that terminal arm. I'm saying it's here. That's 10 pi over 3. That is not the root 2 over 2, root 2 over 2 thing. It's the 1/2 root 3 over 2, which is a half. Well, looking at that, I can see x is a half, even if my drawing isn't perfect. And y is root 3 over 2. These are both negative in quadrant 3. Partway through this lesson, I wanted to maybe pick up the pace, but the unit circle is this important that I would rather go almost to the end here, that you get a good handle on it. We're going to keep revisiting all of this information, but in the meantime, you have some questions on the following page. This is a nice summary of what we've learned today. Try, when you get questions where you have to go to the coordinates of the unit circle, try to resist the temptation of grabbing that sheet. That sheet was a learning exercise, not something that you're going to rely on.